In mathematics, a cubic function is a function of the form where a is non-zero. Or in other words, a function defined by a polynomial of degree 3. The derivative of a cubic function is a quadratic function. The integral of a cubic function is a quartic function. Setting e, x, a equals a0 produces a cubic equation of the form. Usually, the coefficients a, b, c, d are real numbers. However, most of the theory is also valid if they belong to any field of characteristic other than 2 or a 3. To solve a cubic equation is to find the zero of a cubic function. That is to say, to find a particular value of x for which e, x, a equals a0. There are various ways to solve a cubic equation. The solutions, also called roots, of a cubic equation can always be found algebraically. This is also true of a quadratic or quartic equation but no higher degree equation by the Abler-Euro-Ruffney theorem. The roots can also be found trigonometrically. Alternatively, one can find a numerical approximation of the roots in the field of the real or complex numbers. This may be obtained by any root-finding algorithm, like Newton's method. Solving cubic equations is a necessary part of solving the general quartic equation, since solving the latter requires solving its resultant cubic equation. History: cubic equations were known to the ancient Babylonians, Greeks, Chinese, Indians, and Egyptians. Babylonian cuneiform tablets have been found with tables for calculating cubes and cube roots. The Babylonians could have used the tables to solve cubic equations, but no evidence exists to confirm that they did. The problem of doubling the cube involves the simplest and oldest studied cubic equation, and one for which the ancient Egyptians did not believe a solution existed. In the 5th century BC, Hippocrates reduced this problem to that of finding two mean proportionals between one line and another of twice its length, but could not solve this with a compass and straight construction, a task which is now known to be impossible. Methods for solving cubic equations appear in the 9 chapters on the mathematical art, a Chinese mathematical text compiled around the 2nd century BC and commented on by Liu Hui in the 3rd century. The ancient Greek mathematician Diophantus found solutions for indeterminate cubic equations in the 3rd century. Hippocrates, Menaechmus and Archimedes are believed to have come close to solving the problem of doubling the cube using intersecting conic sections, though historians such as Revionetz dispute whether the Greeks were thinking about cubic equations or just problems that can lead to cubic equations. Some others like T. L. Heath, who translated all Archimedes' works, disagree, putting forward evidence that Archimedes really solved cubic equations using intersections of two cones, but also discuss the conditions where the roots are 0, 1 or 2. In the 7th century, the Tang dynasty astronomer-mathematician Wang Xiaotong in his mathematical treatise titled Jigai Sfunjing systematically established and solved 25 cubic equations of the form, 23 of them with, and 2 of them with. In the 11th century, the Persian poet-mathematician, Omar Khayyam, made significant progress in the theory of cubic equations. In an early paper he wrote regarding cubic equations, he discovered that a cubic equation can have more than one solution and stated that it cannot be solved using compass and straight constructions. He also found a geometric solution. In his later work, the Treatise on Demonstration of Problems of Algebra, he wrote a complete classification of cubic equations with general geometric solutions found by means of intersecting conic sections. In the 12th century, the Indian mathematician Bhaskara too attempted the solution of cubic equations without general success. However, he gave one example of a cubic equation. In the 12th century, another Persian mathematician, Sharif al-Din al-Tazar, wrote the Al-Mu'adalat, which dealt with 8 types of cubic equations with positive solutions and 5 types of cubic equations which may not have positive solutions. He used what would later be known as the Ruffney-Horner method to numerically approximate the root of a cubic equation. He also developed the concepts of a derivative function and the maxima and minima of curves in order to solve cubic equations which may not have positive solutions. He understood the importance of the discriminant of the cubic equation to find algebraic solutions to certain types of cubic equations. Leonardo da Pisa, also known as Fibonacci, was able to find the positive solution to the cubic equation x3 plus a2 x2 plus a10 za equals a20, using the Babylonian numerals. He gave the result as 1, 22, 7, 42, 33, 4, 40, which differs from the correct value by only about 3 trillionths. In the early 16th century, the Italian mathematician Scipione del Ferro found a method for solving a class of cubic equations, namely those of the form x3 plus mx equals n. In fact, all cubic equations can be reduced to this form if we allow m and n to be negative, but negative numbers were not known to him at that time. Del Ferro kept his achievement secret until just before his death, when he told his student Antonio Fiore about it. In 1530, Nicola Square Tartaglia received 2 problems in cubic equations from Jean d'Arcueil and announced that he could solve them. He was soon challenged by Fiore, which led to a famous contest between the two. Each contestant had to put up a certain amount of money in to propose a number of problems for his rival to solve. Whoever solved more problems within 30 days would get all the money. Tartaglia received questions in the form x3 plus mx equals n, for which he had worked out a general method. Fiore received questions in the form x3 plus mx2 equals n, which proved to be too difficult for him to solve, and Tartaglia won the contest. Later, Tartaglia was persuaded by Gerolamo Cardano to reveal his secret for solving cubic equations. In 1539, Tartaglia did so only on the condition that Cardano would never reveal it, and that if he did reveal a book about cubics, that he would give Tartaglia time to publish. Some years later, Cardano learned about Ferro's prior work and published Ferro's method in his book Ars Magna in 1545, meaning Cardano gave Tartaglia 6 years to publish his results. Cardano's promise with Tartaglia stated that he not publish Tartaglia's work, and Cardano felt he was publishing Del Ferro's, so as to get around the promise. Nevertheless, this led to a challenge to Cardano by Tartaglia, which Cardano denied. The challenge was eventually accepted by Cardano's student Lodovico Ferrari. Ferrari did better than Tartaglia in the competition, and Tartaglia lost both his prestige and income. Cardano noticed that Tartaglia's method sometimes required him to extract the square root of a negative number. He even included a calculation with these complex numbers in Ars Magna, but he did not really understand it. Raphael Bombelli studied this issue in detail and is therefore often considered as the discoverer of complex numbers. Frana section Y via TE independently derived the trigonometric solution for the cubic with 3 real roots, and Rena copyright Descartes extended the work of via TE. Derivative. Through the quadratic formula, the roots of the derivative are euro squared, x, a equals 3x2 a plus a 2bx a plus ac are given by, and provide the critical points where the slope of the cubic function is 0. If b2a3 is 0, then the cubic function has a local maximum and a local minimum. If b2a3 equals a0, then the cubic's inflection point is the only critical point. If b2a3 is 0, then there are no critical points. In the cases where b2a3 parallel 0, the cubic function is strictly monotonic. Roots of a cubic function. The general cubic equation has the form with. This section describes how the roots of such an equation may be computed. The coefficients a, b, c, d are generally assumed to be real numbers, but most of the results apply when they belong to any field of characteristic not 2 or 3. The nature of the roots. Every cubic equation with real coefficients has at least one solution x among the real numbers. This is a consequence of the intermediate value theorem. We can distinguish several possible cases using the discriminant. The following cases need to be considered. If I 0, then the equation has 3 distinct real roots. If I equals 0, then the equation has a multiple root and all its roots are real. If I 0, then the equation has 1 real root and 2 non-real complex conjugate roots. For information about the location in the complex plane of the roots of a polynomial of any degree, including degree 3, See Properties of polynomial roots and the Euro-Hurwitz stability criterion, general formula for roots, for the general cubic equation. The general formula for the roots, in terms of the coefficients, is as follows. Where are the three cube roots of unity, and where? With. And, where is the discriminant discussed above? In these formulae, and denote any choice for the square or cube roots. Changing of choice for the square root amounts to exchanging and. Changing of choice for the cube root amounts to circularly permuting the roots. Thus the freeness of choosing a determination of the square or cube roots corresponds exactly to the freeness for numbering the roots of the equation. 4 centuries ago, Gerolamo Cardano proposed a similar formula, which still appears in many textbooks. Where and is the complex conjugate of. However, this formula is applicable without further explanation only when a, b, c, d are real numbers and the operand of the square root, a, is non-negative. When this operand is real and non-negative, the square root refers to the principal square root and the cube roots in the formula are to be interpreted as the real ones. Otherwise, there is no real square root and one can arbitrarily choose one of the imaginary square roots. For extracting the complex cube roots of the resulting complex expression, we have also to choose among 3 cube roots in each part of each solution, giving 9 possible combinations of one of 3 cube roots for the first part of the expression and one of 3 for the second. The correct combination is such that the 2 cube roots chosen for the 2 terms in a given solution expression are complex conjugates of each other. The next sections describe how these formulas may be obtained. Special cases, if and the sign of has to be chosen to have, that is, one should define whichever is the sign of, if and the 3 roots are equal. If and the above expression for the roots is correct but misleading, hiding the fact that no radical is needed to represent the roots. In fact, in this case, there is a double root and a simple root. Reduction to a depressed cubic, dividing equation by and substituting by, we get the equation where the left-hand side of equation is a monic trinomial called a depressed cubic. Any formula for the roots of a depressed cubic may be transformed into a formula for the roots of equation by substituting the above values for and using the relation. Therefore, only equation is considered in the following. Quedarnos method. The solutions can be found with the following method due to Scipione del Ferro and Tartaglia, published by Gerolamo Cardano in 1545. This method applies to the depressed cubic. We introduce 2 variables u and v linked by the condition, and substitute this in the depressed cubic, giving. At this point Cardano imposed a second condition for the variables u and v. As the first parenthesis vanishes in, we get and. Thus and are the 2 roots of the equation. At this point, Cardano, who did not know complex numbers, supposed that the roots of this equation were real, that is that, solving this equation and using the fact that and may be exchanged, we find, and. As these expressions are real, their cube roots are well defined and, like Cardano, we get. The 2 complex roots are obtained by considering the complex cube roots. The fact is real implies that they are obtained by multiplying one of the above cube roots by and the other by. If is not necessarily positive, we have to choose a cube root of. As there is no direct way to choose the corresponding cube root of, one has to use the relation, which gives and. Note that the sign of the square root does not affect the resulting, because changing it amounts to exchanging and. We have chosen the minus sign to have when and, in order to avoid a division by 0. With this choice, the above expression for always works, except when, where the second term becomes 0/0. In this case there is a triple root. Note also that in several cases the solutions are expressed with fewer square or cube roots, if then we have the triple real root. If and then. And the 3 roots are the 3 cube roots of. If and then. In which case the 3 roots are. Where. Finally, if there is a double root and a simple root which may be expressed rationally in term of, but this expression may not be immediately deduced from the general expression of the roots. To pass from these roots of an equation to the general formulas for roots of an equation, subtract and replace and by their expressions in terms of Vieta's substitution, starting from the depressed cubic. We make the following substitution, known as Vieta's substitution. This results in the equation. Multiplying by W3, it becomes a sextic equation in W, which is in fact a quadratic equation in W3. The quadratic formula allows to solve it in W3. If W1, W2 and W3 are the three cube roots of one of the solutions in W3, then the roots of the original depressed cubic are. Lagrange's method, in his paper Ra copyright Flexions sur la Ra copyright solution alga copyright brick des copyright equations, Joseph Louis Lagrange introduced a new method to solve equations of low degree. This method works well for cubic and quartic equations, but Lagrange did not succeed in applying it to a quintic equation, because it requires solving a resolvent polynomial of degree at least 6. This is explained by the Abler-Ruffny theorem, which proves that such polynomials cannot be solved by radicals. Nevertheless, the modern methods for solving solvable quintic equations are mainly based on Lagrange's method. In the case of cubic equations, Lagrange's method gives the same solution as Quedarnos. By drawing attention to a geometrical problem that involves two cubes of different size, Quedarnos explains in his book Ars Magna how he arrived at the idea of considering the unknown of the cubic equation as a sum of two other quantities. Lagrange's method may also be applied directly to the general cubic equation without using the reduction to the depressed cubic equation. Nevertheless, the computation is much easier with this reduced equation. Suppose that x0, x1 and x2 are the roots of equation or, and define which satisfies the relation. We now set. This is the discrete Fourier transform of the roots. Observe that while the coefficients of the polynomial are symmetric in the roots, in this formula an order has been chosen in the roots, so these are not symmetric in the roots. The roots may then be recovered from the 3C by inverting the above linear transformation via the inverse discrete Fourier transform, giving. The polynomial is an elementary symmetric polynomial and is thus equal to in case of equation and to 0 in case of equation, so we only need to seek values for the other two. The polynomials and are not symmetric functions of the roots, is invariant, while the two non-trivial cyclic permutations of the roots send to and to, or to and to, while transposing and switches and. Other transpositions switch these roots and multiply them by a power of, thus, and are left invariant by the cyclic permutations of the roots, which multiply them by. Also and are left invariant by the transposition of and which exchanges and. As the permutation group of the roots is generated by these permutations, it follows that and are symmetric functions of the roots and may thus be written as polynomials in the elementary symmetric polynomials and thus as rational functions of the coefficients of the equation. Let and in these expressions, which will be explicitly computed below. We have that and are the two roots of the quadratic equation. Thus the resolution of the equation may be finished exactly as described for Quedarnos method, with and in place of and. Computation of A and B, setting, and, the elementary symmetric polynomials, we have, using that. The expression for is the same with and exchanged. Thus, using we get. And a straightforward computation gives. Similarly we have. When solving equation we have, and, with equation, we have, and thus, and. Note that with equation, we have and, while in Quedarnos method we have set and thus we have, up to the exchange of and. In other words, in this case, Quedarnos and Lagrange's method compute exactly the same things, up to a factor of 3 in the auxiliary variables, the main difference being that Lagrange's method explains why these auxiliary variables appear in the problem. Trigonometric method. When a cubic equation has 3 real roots, the formulas expressing these roots in terms of radicals involve complex numbers. It has been proved that when none of the 3 real roots is rational the casus irreducibilis one cannot express the roots in terms of real radicals. Nevertheless, purely real expressions of the solutions may be obtained using hypergeometric functions, or more elementarily in terms of trigonometric functions, specifically in terms of the cosine and arccosine functions. The formulas which follow, due to Frenet section Y via TE, are true in general, are purely real when the equation has three real roots, but involve complex cosines and arc cosines when there is only one real root. Starting from equation, let us set the idea is to choose to make equation coincide with the identity. In fact, choosing and dividing equation by we get. Combining with the above identity, we get. And thus the roots are. This formula involves only real terms if and the argument of the arc cosine is between a 1 and 1. The last condition is equivalent to which implies also. Thus the above formula for the roots involves only real terms if and only if the three roots are real. Denoting by the above value of TO, and using the inequality for a real number U such that the three roots may also be expressed as. If the three roots are real, we have. All these formulas may be straightforwardly transformed into formulas for the roots of the general cubic equation, using the back substitution described in section reduction to a depressed cubic. When there is only one real root, it may be similarly represented using hyperbolic functions, as if par permel a 0 and the inequalities on the right are not satisfied, the formulas remain valid but involve complex quantities. When, the above values of are sometimes called the Chebyshev cube root. More precisely, the values involving cosines and hyperbolic cosines define, when, the same analytic function denoted, which is the proper Chebyshev cube root. The value involving hyperbolic signs is similarly denoted when. Factorization: if the cubic equation with integer coefficients has a rational real root, it can be found using the rational root test. If the root is r equals m/n fully reduced, then m is a factor of d and n is a factor of a, so all possible combinations of values for m and n can be checked for whether they satisfy the cubic equation. The rational root test may also be used for a cubic equation with rational coefficients. By multiplication by the lowest common denominator of the coefficients, one gets an equation with integer coefficients which has exactly the same roots. The rational root test is particularly useful when there are three real roots because the algebraic solution unhelpfully expresses the real roots in terms of complex entities. The rational root test is also helpful in the presence of one real and two complex roots because it allows all of the roots to be written without the use of cube roots. If r is any root of the cubic, then we may factor out using polynomial long division to obtain. Hence if we know one root we can find the other two by using the quadratic formula to solve the quadratic, giving for the other two roots. Geometric interpretation of the roots, three real roots. Via TE's trigonometric expression of the roots in the three real roots case lends itself to a geometric interpretation in terms of a circle. When the cubic is written in depressed form as above as shown above, the solution can be expressed as. Here is an angle in the unit circle. Taking of that angle corresponds to taking a cube root of a complex number. Adding for k equals 1, 2 finds the other cube roots. And multiplying the cosines of these resulting angles by corrects for scale. For the non-depressed case, the depressed case as indicated previously is obtained by defining t such that so. Graphically this corresponds to simply shifting the graph horizontally when changing between the variables t and x, without changing the angle relationships. One real and two complex roots, in the Cartesian plane. If a cubic is plotted in the Cartesian plane, the real root can be seen graphically as the horizontal intercept of the curve. But further, if the complex conjugate roots are written as g plus high, then g is the abscissa of the tangency point of a line that is tangent to the cubic curve and intersects the horizontal axis at the same place as does the cubic curve. And h is the square root of the tangent of the angle between this line and the horizontal axis. In the complex plane, with one real and two complex roots, the three roots can be represented as points in the complex plane, as can the two roots of the cubic's derivative. There is an interesting geometrical relationship among all these roots. The points in the complex plane representing the three roots serve as the vertices of an isosceles triangle. Accessing the other two roots, being complex conjugates, appear symmetrically above and below the real axis. Marden's theorem says that the points representing the roots of the derivative of the cubic are the foci of the Steinerian ellipse of the triangle the unique ellipse that is tangent to the triangle at the midpoints of its sides. If the angle at the vertex on the real axis is less than, then the major axis of the ellipse lies on the real axis, as do its foci and hence the roots of the derivative. If that angle is greater than, the major axis is vertical and its foci, the roots of the derivative, are complex. And if that angle is, the triangle is equilateral, the Steinerian ellipse is simply the triangle's incircle, its foci coincide with each other at the incenter, which lies on the real axis, and hence the derivative has duplicate real roots. Omar Khayyam's solution. As shown in this graph, to solve the third-degree equation where Omar Khayyam constructed the parabola, the circle which has as a diameter the line segment of the positive x-axis, and a vertical line through the point above the x-axis, where the circle and parabola intersect. The solution is given by the length of the horizontal line segment from the origin to the intersection of the vertical line and the x-axis. A simple modern proof of the method is the following: multiplying by x the equation, and regrouping the terms gives. The left-hand side is the value of y2 on the parabola. The equation of the circle being the right-hand side is the value of y2 on the circle. See also, algebraic equation, linear equation, Newton's method, polynomial, quadratic equation, quartic equation, quintic equation, spline, notes. References: Anglin, W.S. Lambeck, Joachim, Mathematics in the Renaissance, The Heritage of Thales, Springers, ppA 125 131, ISBN A978-0-387-94544-6 ch24. Dents, T., Cubics, Chaos and Newton's Method, Mathematical Gazette 81, 403 408, doi, 10.2307/3619617, ISNA 0025-5572 Dunnett, R., Newtona Ralphson and the Cubic, Mathematical Gazette 78, 347 348, doi, 10.2307/3620218, ISNA 0025-5572 Guilbeau, Lucy, The History of the Solution of the Cubic Equation, Mathematics Newsletter 5, 8/12, doi, 10.2307/3027812, JSTORA 3027812 Jacobson, Nathan, Basic Algebra 1, Dover, ISBN A978-0-486-47189-1 Mitchell, D.W., Solving Cubics by Solving Triangles, Mathematical Gazette 91, 514 516, ISNA 0025-5572 Mitchell, D.W., Powers of I as Roots of Cubics, Mathematical Gazette 93, A. ISNA 0025-5572 Press, W.H. Tucholsky, S.A. Bettling, W.T. Flannery, B.P., Section 5.6 Quadratic and Cubic Equations, Numerical Recipes, The Art of Scientific Computing, New York, Cambridge University Press, ISBN A978-0-521-88068-8. Retzschaffen, Edgar, Real Roots of Cubics, Explicit Formula for Quasi-Solutions, Mathematical Gazette 92, 268 ISNA 0025-5572 Zucker, I.J., The Cubic Equation A New Look at the Irreducible Case, Mathematical Gazette 92. 264 268, ISNA 0025-5572 External links, Haswinkel, Michiel, ed., Cardano Formula, Encyclopedia of Mathematics, Springer, ISBN A978-1-55608-010-4. Solving a cubic by means of Moebius transforms, interesting derivation of trigonometric cubic solution with 3 real roots, Calculator for solving cubics, Tartaglia's work on the solution of the cubic equation at convergence, cubic equation solver. Quadratic, cubic and quartic equations on Makshta archive. Cubic formula at planetmath.org. Cardano solution calculator as Java applet at some local site. Only takes natural coefficients. Graphic explorer for cubic functions with interactive animation, slider controls for coefficients, on solution of cubic equations at Holistic Numerical Methods Institute, Dave Aukley, solving the quartic with a pencil. American Math Monthly 114-129 €39, cubic equation by Eric W. Wellerstein, The Wolfram Demonstrations Project, 2007. The Cubic Tutorials by John H. Matthews.